Hello everyone, I am Kuntal Pandya from Samsung Semiconductor India Research. Today I will be giving poster presentation on a novel approach for verifying high-speed and power-efficient MIPI-MPHY 5.0 IP by upgrading conventional MPHY test bench. I would like to thank my co-authors Eldhose, Sagar, Suraj, Parag, and DVCon U.S. for giving me this opportunity. This poster is about various techniques used in verifying high-speed SerDes interface for mobile protocol, that is MPHY IP. The areas which we have identified for enhancements are incorporating changes related to 5.0 specification. Second one, how to make setup reusable, scalable, and efficient. With the implementation of industry-derived CDS scenarios like real-time loopback, serial data frequency check, slew rate checks, etc. The other areas are related to interface connectivity check, stress test for CDR module, how to achieve faster functional coverage, and we have also emphasized on optimizing regression runtime by meeting time to market. Any typical SerDes architecture consists of parallel and serial interface. MPHY design has two blocks, PCS, which is connected to parallel interface, whereas PMA is connected to serial interface. The UVM environment comprises of an agent, driver, monitor for driving MPHY 5.0 specification related transactions, and scoreboard is used for data integrity check. That is from the third-party VIP. The coverage block is capturing how much a design has been exercised as per test plan. For verifying any SerDes protocol, this is not enough. So we have identified certain areas for an additional check. High impedance and unknown checkers are applied at parallel and serial interface. Protocol timing related checks has been done at input-output interface of PCS PMA and internal blocks of PMA. A jitter module has been introduced in the test top for exercising CDR block of PMA receiver. Noise injection scenarios for verifying design more robustly. Based on enhancements done in the test bench architecture and the sequence logic, we have achieved following results. Total 73 signals are present in the PCS PMA and analog digital block of the PMA. 3 kinds of checks has been applied. With formal connectivity check, we have got 2 bugs, 6 bugs with X and Z checker, and 23 bugs related to timing protocol. Second technique is focused on making test bench more reusable and scalable. As per specification, each MPHY state is converted to a sequence for simplifying the execution of various scenarios. Hence, avoided to have a redundant code. Coming to the jitter-based verification for the CDR module. Any serial data tend to get distorted with external noise, jitter, SSC, PPM, etc., which could lead to a data loss. So, we have implemented jitter module, which generates a block with all sort of distortion, and based on it, data has been sampled and fed to RX serial interface. With this, we have thoroughly verified CDR module and concluded that design works well within the limit. Any verification cycle is incomplete without achieving 100% functional and code coverage. Here we have applied 2 techniques for faster coverage. The relevant set of test suites are given as an input to a script, which generates an output file with a list of test cases majorly contributing to the coverage. The second method applied is based on array-based coverage collection. Before starting the test execution, all random variables are mapped to an individual array, and during post-randomization phase, a check has been done to identify expected value has been covered or not. Hence, this is how we have achieved faster functional coverage. Optimization of regression runtime was always a high priority. So, in the specification, we have identified the common sequence which is needed for almost 90% of the scenario. We have used snapshot feature of a simulator, that is save and restore method, with which we are able to achieve 15% reduction in the total regression time. A PN module comprises of an analog and digital block. And most of the verification is more focused towards a digital block. So in this step, we have also verified analog module as well, where analog part of the design has been modeled to mimic the digital functionality. With this, we have verified eye monitor module by sweeping voltage and the phase in steps as defined in the protocol, and achieved the end result has been plotted in the form of graph. This technique can be applied to offset calibration, CDR, and DFE modules of the PMA block as well. The last technique which has been implemented is to make test bench efficient for debugging regression failures. Command line switches are applied to reproduce scenarios for faster, scenarios faster by using $values, $+args API. This not only helped us in reproducing scenario for debugging failures, but also to optimize the randomization in more arranged manner. So having said this, we are very proud to successfully execute the plan and achieve the desired results, which helped us in identifying the critical bugs. Moreover, most of the techniques can be applied for any other SerDes protocol, that is USB, PCI, etc. There is always a room for improvement, and further enhancement in the specification has given us a scope to think about the future. We have also planned to implement PRBS7 and PRBS15 pattern generator to our environment, with an additional improvement for coverage module and other blocks. Thank you.